Why is that? He said, I don't know. Maybe the general is a general in charge of DARPA. He thought all M's should be together. So he says, it's a good life. I have no money to give. I have nothing to do. I just wander around listening to seminars. The seminars were about manufacturing. Because again, this was the time that, as they said, the Japanese were eating their lunch by Sony and all these companies beating the Americans. Plus, they were interested in special materials for stealth aircraft, composite materials. But they had no way of really, they were all sort of designed by chemistry and so on. They had no way of manufacturing them. He told me, I listened to this, and it's like the old way of making steel. You heat it, you beat it, and then you hope that it... So he says, but I know that you work in control theory and signal processing. Don't you think those ideas should be helpful in manufacturing? I said, sure. Control theory will control it. He said, Tom, I have no money for mathematics, but I have money for manufacturing, or I can get you money for manufacturing. So I said, Lou, I was disappointed. I said, Lou, that's very kind of you, but I only write papers. And if you do manufacturing, you have to do something. So, he persisted. He said, no, it is challenging and so on. You can do it. You want money? I can give you plenty of money. And you pick any problem in manufacturing that you want. I don't care. It's fine. And finally, he said, it doesn't matter if you fail. Just do it. So with those kinds of challenges, and $2 million for 3 years, it's a pretty good challenge. Then the CIS came in handy, because by then it was a well-established lab. So we went over there, and we found a problem where we could contribute. So let me tell you the story. So this is, anyway. For example, a year after we started, I went to MIT to give a seminar on our work. And I noticed this in the mechanical engineering department. Papkin de Terosian was chairman of Silicon Valley Group, which is a leading company in manufacturing of semiconductors. And his title was Manufacturing is Moving Center Stage in the 90s. So it was a good time to enter manufacturing. Here is what we found. There was a project that Texas Instruments had, given by the Air Force, a demonstration project, to explore a new method for making semiconductors. Okay. And they had given a subcontract to a group because the person at TI was a student of Professor Saraswat at Stanford. So they gave a subcontract to CIS. And here is the proposal. I won't go into it. But the traditional method of making semiconductors is you have a big oven and you put all these wafers, a large number of them in the oven, and you heat it for a certain number of hours and so on, and you bake do the processes in there and you get the chips. They said, it's time consuming, you need clean rooms, it's expensive. People had come up with the idea of single wafer manufacturing. You have a small vacuum chamber about 6 inches high and maybe a foot in diameter. You put one wafer at a time with a robot arm in a vacuum. You don't need a clean room, just this has to be vacuum. You process it as quickly as you can with oxidization or annealing or whatever. Move it out, move the next chip in, and so on. So you have a cluster of these single wafers, and you go through the process. But show the feasibility. They give a 4-year project, and you have to demonstrate, I think, in May 93, with a certain run that this method will work. So we came in about a year into this project, and we found the following. This is the processor that they had. This is the vacuum chamber. How do I get the light? Okay, yeah. So you put a wafer here. Whatever plasmas or whatever you want to process is over it. They heat it. Excuse me. They heat it with an arc lamp, and that does the processing. What you have to do is follow certain trajectories. So let me show you. For example, this is what you have to do. You take a wafer at room temperature. You have to heat it as quickly as you can to 1,000 degrees. Hold it steady for varying amounts of time. Then cool it as rapidly as you can and do the next step. Now, what does it mean as quickly as you can? If you heat it too quickly, it warps. So if you cool it too quickly, it can warp. Secondly, this temperature profile has to be followed precisely for every wafer, because otherwise you'll get unreliable results. Moreover, so precise trajectory following is needed. Moreover, you want uniform, the whole wafer must be heated uniformly. The wafer has many, many dies with chips on it. The chips, the boundaries may not get the same quality as the others and so on. So this is the challenge, how to do it. Now, the conventional wisdom was that in order to get uniform temperature across the wafer, the heat flux on the wafer must be uniform, because it's the heat flux that heats it. So all the efforts were to try and get uniform heat flux, but they failed, actually. And this is the kind of profile you get. No matter what they did, the edges were not coming out right. We said that because, it's not just heat. There's radiation from the wafer. There's reflection from the walls of the chamber. There's convection, the gas is passing over, and so on. You are not taking these into account. What they were doing is, they had different, for example, there were lots of small companies making these heating lamps. One was you had a specially designed reflector, so you had the heat source here and reflected so that you get uniform wafer. And this was called Peak Systems. Another company was AG Systems. They had one bank of lamps above the wafer going in one direction, and below it, another bank going in the opposite, one going this way and the other going this way. But no matter what they did, it wasn't working. That's when we entered the picture. So as I said, it was this time that we received the DARPA challenge, and were lucky to find Saraswat had been working for a year on this project. So a team of my colleagues, and especially students, fresh students, we knew nothing about manufacturing. We began to look at this project, and I also had a postdoc who had chemical engineering, which was useful because there's a lot of chemistry that goes into making these wafers and all kinds of language. CVD, poly, RTO, do you know what that is? Rapid thermal oxidation, and so on. So the approach that people had was empirical, based on trial and error to tweak the control parameters. It was not untypical of the industry at that time. We took a different approach. We said, let's make a mathematical model. And the simplest model is, moreover, apart from this problem, they had only one control variable, because control device was supplied by another small company. The semiconductor people didn't know what was inside the box. It only said, do not open. And you had one knob which controlled the resistance and the heat. But in control theory, you have multivariable control. You have many control variables. Anyway, so we thought that was inadequate. Instead of a wafer, we made a rod. And we said, can we heat a rod uniformly? It's one-dimensional instead of two-dimensional. And we found with one control variable, you could not do it. You needed at least 2 or 3. And then with the wafer, so we said first thing is you need multivariable control. Secondly, the mathematics shows that you do not need uniform flux on the wafer. It has to be non-uniform because there are all these other effects which interact with it. So you have a different profile which has to be used for different steps. So how do you do it? Well, it turns out we were lucky again. By the way, you get a lot of respect, despite what I'm saying, a great deal of respect for experimental work and experimental engineers. You need infinite patience. A part breaks, You have to wait 1 month for a new part to come, and so on and so forth. And many people won't allow you to use their equipment because they say you'll damage it. So then they train you for 2 weeks, etc. However, so this was our systems approach, just to say, first step is abstract and simplify a real-world problem so you can make a mathematical model for it. Okay. Then one uses and sometimes develops from scratch a variety of often surprisingly advanced math tools to solve the problem. Once you have the mathematical result, you see that's not ready for